Welcome to Theory of Computation. This is lecture number 16. In the last lecture, we started studying decidability in logic. As I told you, logic is a branch of mathematics that studies mathematics itself. It looks at what proofs are, what are theorems, how can we prove things. It asks questions like whether everything is true, which is true, is provable or not, and whether we can come up with decision procedures for proving statements. Today's lecture is going to be a continuation on decidability in logic. The overview of today's lecture is as follows. Today we will start with decidability in logic. We will review the definitions, and then we would look at something called Presburger's arithmetic. After doing that, we will prove that statements in Presburger's arithmetic are decidable, which means that we can find an algorithm which can take any sentence in this arithmetic and tell us whether it is true or not. So we will see an example of a decidable theory of logic. Let's begin. Let's review our definitions that we started with. Remember, we started with a language. This language consisted of the usual symbols for variables, x. It also consisted of the symbols for and, or, and not, the logical connectives. Then there were two quantifiers, for all and there exists. And lastly, we had a list of relation symbols, R1 up to Rk. Using these things, we were able to make strings, and we defined what a well-formed formula was. Once we had well-formed formulas, we have a syntax of writing down statements. But these statements have no meaning. Let's look at it. So we have the alphabet, which consists of a symbol for or, and, not, two parentheses. They exist for all x, R1, R2, all the way up to Rk. And then we considered formulas. We formally define what formulas are. So we will not go through the definition again. Let's just look at two formulas. The first formula here is there exists x1 for all x2, R1 of x1, x2 or R2 of x1, x3. This formula has one free variable, that is x3. x1 and x2 are not free variables. The second example is for all x1, for all x2, there exists x3, R2 of x1 or then in brackets R3 of x1, x3 and R1 of x2, x2. This is also a formula. This has no free variables. Therefore, we say that this formula is a sentence. So, what we can do is make formulas, and we have a syntax for making formulas. But these formulas have no meaning. Therefore, the question of these formulas being true or not, or the sentences being true or not, does not arise. What we need to do is give this structure some semantics. So we have to come up with the meaning of what these formulas are. In order to do that, firstly, we have to specify two things. First, we specify a universe. The universe says these are the values that the variables can take. Once we have specified the universe, we also need to specify what each relation symbol means. So for each relation symbol, we actually take a real relation and associate that relation with the relation symbol. Once we do that, we get a language over this model. So a model is a universe along with relation symbols. A sentence is any formula which has no free variables. Here's an example of a sentence. For all x1, there exists x2, R1 of x1, x2 and R2 of x2, x1. Here's another sentence. For all x, R1 of x, x. A sentence does not have any free variables, and therefore, if we have a model and a sentence, then either that sentence is true in that model or it is false. To specify a model, we have to specify U, the universe where the variables will take values, and each relation symbol is assigned a real relation over that universe. So if P1, P2, Pk are relations over the universe, they are assigned to symbols R1, R2 up to Rk. Once we have assigned the relations, we have a model. Now we can look at sentences over this model, and these sentences are either true or not. Let's look at an example. The language of the model is the set of all formulas which use the relation symbols with correct arity. Suppose in the model M, R1 is assigned a binary relation P1, so the arity of P1 is 2. R2 is assigned a unary relation P2, so the arity of P2 is 1. R3 is assigned a fiveary relation P3, so its arity is 5. Then let's look at this formula. For all x1 there exists x2, R1 of x1, x2, so R1 is used as a binary relation, so its arity is correct, or R2 of x4, since R2 is assigned a unary relation, its arity is correct, and R3 of x2, x1, x3, x4, x5, and its arity is also correct. So this formula is in the language of the model. On the other hand, the next formula that's written on the screen, for all x, there exists x2, R1 of x1, or R2 of x4, and R3 of x2, x1 is not in the language because the arity of two of the relations is wrong. So once we have a model and each relation symbol has been assigned a real relation, then we are only interested in formulas which have the correct arity. Each Ri has the correct arity in the formula in all its occurrence. That defines the language of the model. Once we have defined the language of the model, some of the statements will be true in that model, others will not be true. If M is a model, we let th of M denote the theory of M. It is by definition the set of all sentences that are true in the language of M. A central point of investigation is to find out which theories are decidable and which ones are not. So, once you have a model, you can look at any sentence in the language of that model and it will be either true or not. If you collect the set of all sentences which are true, that is what we will call the theory of that model. And what we want to know is whether that theory is a decidable set or not. What we would like to know is if there is an algorithm that can tell us if a sentence is true in that model or not. Let's look at a few examples. Note that when we are talking about a model in which the relations have some usual meaning, then we can shift to infix notation. We also saw examples of sentences that are true in one model and false in another model. Let's review one of them. Phi is the sentence, for all y there exists an x, R1 of x, x, y. So this is a sentence. Now we look at the model M1. This is the model where the universe is the set of all natural numbers and R1 is assigned the meaning of plus. Since we can add natural numbers, we can assign this relation R1 the meaning of plus. Then the sentence can be rewritten and it's easier to read. It says, for all y there exists a x such that x plus x equals y. So x plus x equals y, well, we can infer from that y is equal to 2x, and so we infer from that y must be an even number. So this sentence says, for all y, y is an even number, and that is not the case in integers or natural numbers, and therefore this sentence is false in the model. However, we can look at this sentence in another model. So let's look at this sentence in the model where the universe is the set of all real numbers. R1 is again assigned the usual meaning of plus. Then the sentence, if we rewrite it in fixed notation, says, for all y, there exists a x such that x plus x equals y. So for all y, y is equal to 2x. So we can find a x, which is y over 2, which satisfies this sentence, and thus it's true that all real numbers are 2 times some other real number. So this sentence is true for real numbers with the usual meaning of plus, but it's false for natural numbers with the usual meaning of plus. So in order to say whether a sentence is true or not, we must look at the model. it would depend on the model. A sentence can be true for one model, but false for the other model. Once we have a model, we have actually given meaning to our sentences and they become true or false. Given a model M, we would like to know which sentences are true and which ones are not true. What we want is a decision procedure or an algorithm which will take a sentence and tell us if the sentence is true or not. So what we want is to write a program, and that program we can give it a sentence as an input, and the program should analyze that sentence, and after doing certain amount of analysis, the program should output whether the sentence is true or not. If we can find such an algorithm, if we can write such a program, then we say that the theory is decidable. However, if we cannot do that, then we say that the theory is not decidable. One of the most interesting model is number theory, where M consists of the natural numbers and the relation plus, multiplication, equality, less than or equal to with their usual meaning. Number theory is extremely interesting model, and we can write sentences in number theory. In the previous class, we actually looked at 3 sentences in number theory. One of them was saying that the number of primes is infinite. That statement is true and it was proved by Euclid. Another one was saying that a to the n plus b to the n equals c to the n has no integer solution in positive integers for n greater than or equal to 3. That statement is Fermat's last theorem and has a very difficult proof. And the last statement was saying that there are arbitrarily large twin primes, and that statement is still open. No one knows whether it's true or not. Number theory is an extremely interesting theory. Unfortunately, number theory is undecidable. This theory is undecidable. There cannot be an algorithm which takes a statement in number theory and tells us whether the statement is true or not, which you would have expected, because if number theory were decidable, then we could take the statement, the twin prime conjecture, and give it to that algorithm, and instead of working on it ourselves, we could let the algorithm work on it, and after some amount of time it would eventually tell us whether that statement is true or not. So on one hand, number theory is not decidable. That seems like it's bad news. On the other hand, it's good news for us because we have so many interesting problems to work on. We will prove in this class that this theory is not decidable. But before going to undecidability of theories, why don't we first look at a theory which is decidable? Let us start with a simpler theory. This theory is called Presburger arithmetic, and the universe once again is natural numbers. There are 2 relations, one is plus and the other is equality with their usual meaning. So only multiplication is missing in Presburger arithmetic. What kind of sentences can we write in Presburger arithmetic? Well, you can write formulas which use plus and it uses equality. So for example, x plus y equals z is a formula in Presburger arithmetic. You could also write things like 2x plus y equals z by writing x plus y equals z. However, you would not be able to write x times y is equal to z because multiplication is not a relation symbol in Presburger arithmetic. Let's look at some sentences in this arithmetic. For all y, there exists an x such that x plus x equals y. This is a sentence in Presburger arithmetic. Another sentence is, for all x, for all y, there exists a z such that x plus y equals z and x plus y equals z, or x plus y equals z plus z plus z. Note that it is possible to write 5x as x plus x plus x plus x plus x. However, we cannot write x times y or x squared. So, in this theory, variables can be only multiplied with constants. We cannot use higher powers either. So, sentences or formulas in Presburger arithmetic are really simple. They are not as difficult as when you allow multiplication. If you allow multiplication, then you can express many interesting concepts and difficult concepts such as a number is prime, or things like there are infinitely many primes. However, these sentences cannot be expressed in Presburger arithmetic because multiplication is not a relation symbol and it's not allowed. So these sentences or formulas are a lot simpler than in number theory. We want to prove that this theory is decidable. So we want to design an algorithm or a Turing machine which takes as input a sentence and decides if it is true or not. How does the input look like? Well, the input would look like for all y, there exists a z, there exists a x, such that x plus x equals y or y plus x equals z. Another possible input could be for all x, for all y, there exists a z, such that z plus x equals z plus y, and not of y plus x equals z plus z. How would an algorithm decide if a sentence is true? Well, a very simple idea comes to our mind. Suppose that there was a formula which was very simple. It was of the kind, there exists a x, and some formula which was quite complicated. What we can do is we can take x equals 1, plug it in, and see if we get a true statement, x equals 2 and plug it in, and so on. But this is not going to work because there are infinitely many integers. So this simple idea may lead us to a way of recognizing true statements, but it will never lead us to deciding whether they are true or false. We are going to run into other problems also, so that's not a good idea. The proof that Presburger arithmetic is decidable is actually extremely non-trivial, and it uses ideas from the theory of finite automata to prove or come up with an algorithm that decides statements in Presburger arithmetic. Let us start with something simple. Let's look at a simple atomic formula. Remember what an atomic formula was? It has no logical connectives and it does not use any quantifiers. So and it's just one simple relation. So we have a formula x plus y equals z. Can we design a DFA that accepts x, y, z or some suitable encoding of them if and only if they satisfy this equation? So we have a simple equation x plus y equals z, and what we want to do is we want to design a deterministic finite automata, not a Turing machine, but a DFA. A DFA which will accept strings which encode x, y, and z such that x plus y equals z. So how can we give three numbers as input to DFA? Well, one idea is that we write x followed by a comma followed by y and then z. And then what we want is that this DFA should accept this string if and only if x plus y is equal to z. But this idea does not work. However, we can come up with a different way of giving the input to a DFA and make it accept all those strings which represent x, y, and z which satisfy this equation. The idea is you want to give all these strings in parallel to the DFA, so you have to increase your alphabet size. Let's look at this more clearly. How the input be given to the DFA? What we do is we define an alphabet called sigma 3, and this alphabet sigma 3 consists of 8 characters. Each character represents the 3 possible bits of the 3 numbers. So for example, the first character represents 0, 0, 0. That means this particular bit of x is 0, of y is 0, and z is 0. Similarly, it has a character which is represented there by 0, 1, 1. This means this particular bit of x is 0, but this particular bit of y is 1, and this particular bit of z is also 1. Now we can give the input to this DFA. The way we give it input to the DFA is we take this alphabet and make a string out of this alphabet. And as we read the top row, that is x written in binary. and as we read the middle row, that is y written in binary, and as we read the last row, that is z written in binary. So this is like giving the DFA x, y, and z in parallel. So if it is reading the 7th symbol, it's reading the 7th bit of x, the 7th bit of y, and the 7th bit of z. So take an example. Here x equals 5, y equals 3, and z equals 6. Then the input to the DFA would be, the first character will be 101, the second character would be 011, the third character would be 110. The top row reads 101, which is x in binary because x equals 5. The second row reads 011, which is y in binary because y equals 3. The third row reads 110, which is z in binary because z is equal to 6. So we have this special alphabet, and it allows us to give 3 numbers to our DFA D. So the DFA D will accept a language over sigma 3 star. What is the language we want this DFA to accept? We want it to accept all those strings such that those strings represent x, y, and z, such that x plus y equals z. Remember now, if you write any string over that alphabet, you can read its top row and call it x, you can read its middle row and call it y, and you can read its last row and call it z. Can we design a DFA where the input alphabet is sigma 3 and it accepts a string I in sigma 3 star such that the top row of the string, when added to the second row of the strings, gives us the last row of the string? Of course, we are interpreting everything in binary. So our goal is to make a DFA which, when we give it a string over this alphabet, will accept if and only if x plus y is equal to z. Can we make such a DFA? Well, let's first think about how we would solve the problem. If I were to give you x, y, and z and ask you to check if x plus y is equal to z, what you would do is you would start from the left side, you'd keep adding the 2 bits of x and y and checking if they are the same as what you expect, what is written in z, and you would move from the right side to the left. Okay? However, a DFA moves from the left side to the right, and it never comes back. It cannot go back and look at the input once again. So what we can do is we can use the similar idea, that the way we add, to construct this DFA. The answer is yes, but it is easier if the machine is given the strings in reverse. Let's first see how we add in binary. Let's add these 2 numbers 0, 1, 0, 1, 0, 0 and 0, 0, 1, 1, 1, 1, 1. The way we add numbers is we remember the carry and compute the next digit and keep moving to the left. We never go back and change anything. Adding is a very simple algorithm. If the numbers were given to us in reverse, we will remember the carry and keep moving to the right. So if these numbers were given to us in reverse, then this is how I would add them. First, I will set the carry to be 0 and work on the first bit. The first bit of x is 0 and the first bit of y is 1. So they add to 1 and the carry is still 0. The second bit of x is 0 and the second bit of y is 1. So they add to 1 and once again there is no carry. When I work on the third bit, both of them have 1s. So the answer is 0, but now the carry is set equal to 1. After that, the answer is 0 and there is a carry. And in the last case, the answer is 0 and there is no carry. So the answer eventually turns out to be 1, 1, 0, 0, 0, 1. So adding 2 numbers in reverse is extremely simple. You just keep moving to the right and keep adding the bits, remembering the carry. We can use this idea now to make a DFA. This DFA is going to have very few states. It's just that the alphabet it's working on has a lot of characters. So we need to figure out what to do when each one of those characters is seen as an input. This DFA is going to have a start state, which is going to be Q0, and another state Q1, and there's going to be one reject state, which is a trap state. Once the machine goes into it, it would never come out. Let's look at this DFA in detail. Now, this DFA is trying to check if x plus y is equal to z. So in some sense, what we want to do is we are given three numbers. One is x, the other is y, and the third one is z, and somebody is claiming that z is equal to x plus y. So we can, as we add x plus y, we can check it with z and keep going along. This DFA is very simple. It has two states, Q0, Q1, and a trap state, which is a reject state, QR. Q0 is the accept state, Q1 is also an accept state. All we have to do is describe the transition. When the machine is in Q0, the carry is 0. When the machine is in Q1, the carry is 1. So the two states are simply remembering what the current carry is. Since we start with no carries, therefore the start state of the machine is Q0. Now let's look at the transition function of this machine. Delta of Q0 on 0, 0, 0 is equal to Q0. Why is that? Because if the bit of x is 0 and the bit of y is 0, then the bit of the answer would be 0 and there will be no carry. So in this case, the machine remains in state Q0, remembers that there is no carry, and it's first successfully checked that x plus y is equal to z for that particular bit. Let's look at what the transition function does further. Delta of Q0 on the 0, 0, 1 is equal to QR. Why is this? Because if the bit of x is 0 and the bit of y is 0, and there is no carry, then the bit of z should also be 0. In this case, the machine has encountered that this bit of z is wrong, so it goes into a reject state, and the reject state is a trap state, so the machine will reject any input which has this input to it. Similarly, delta of Q0 on 0, 1, 0 is QR. Once again, if you have no carry, the first two bits do not add up to the last bit. Delta of Q0 on 0, 1 is 1 because the first two bits add up to the last bit. Delta of Q0 on 1, 1 is equal to Q1. In this case, as you can see, the first two bits do add up to the last bit. However, there's a carry. So the machine changes its state and goes to Q1 because 1 plus 1 is 0. So the z has the correct bit, but there is a carry. So the machine goes into state Q1. Similarly, we can figure out what the transition function should do when it's in the state Q1. So for example, what would delta of Q1 be on the symbol 0, 1, 0? Well, remember we have one carry. In this case, 0 plus 1 plus the carry is actually 0 plus 1 carry. So the bit has been checked and it's correct, and there is a carry, so the machine will remain in the state Q1. In your handout, you're given all the details of how this DFA works. So we can make a DFA that accepts all strings I such that the top row of I read in reverse binary plus the second row of I read in reverse binary is equal to the last row of I read in reverse binary. Thus, if L represents three numbers x, y, and z, then the DFA accepts I if and only if x plus y equals to z. So we have been able to successfully make one DFA. Remember that x plus y equals z is a formula in Presburger arithmetic. This DFA has the property that it accepts strings which represent numbers, three numbers, which satisfy this formula. This is a very interesting DFA and it is very useful. Let's see what we have actually proved. What we have shown is that we can make a DFA which accepts all strings I in sigma 3 star such that the top row of I read in reverse in binary plus the second row of I read in reverse in binary is equal to the last row of I read in reverse in binary. Thus, if I represents three numbers x, y, and z, then the DFA accepts I if and only if x plus y equals z. But this is just one formula in Presburger arithmetic. In Presburger arithmetic, we can write more complicated formulas. We can write other formulas. What about them? Is it true that we can always make a DFA that would accept those strings which represent numbers which satisfy that formula? That's a very interesting question. Let's look at a slightly more complicated formula. Let's look at the formula x plus y is equal to z plus t. So this formula is saying x plus y is equal to 2z plus t. So it's a different formula, and what we would want to do is something similar to what we did before. Previously we made a DFA. Now also what we will do is we'll make a DFA that would accept those four numbers x, y, z, and t which satisfy this formula. But in order to do that, we will use a similar trick. Now, what we will do is we will work with a different alphabet. This alphabet is going to be larger, and each character of this alphabet is going to represent the 4 bits of the numbers that we are interested in. Let's look at it. Let sigma 4 be this alphabet which has all these characters which are, so each character can be thought of as a column of size 4, and we place all possible zeros and ones in it. So there will be 2 to the 4 characters in this alphabet. Once we look at a string I over sigma 4 star, that naturally represents 4 numbers x, y, and z written in binary or reverse binary. In this case, we will think of these numbers as written in reverse binary. Can we make a DFA D such that D accepts I if and only if x, y, and z satisfy this equation, x plus y equals z plus t. So what we want to do is now make a new DFA which corresponds to all numbers that satisfy this formula. We can use the same trick as we did before to make this DFA. In this case, the machine, what it has to do is add up the bits of x plus y and take the bit of z, double that, and add it to the bit of t and check if the answer is the same. And it can keep moving to the right and keep checking that till it comes to the end of the input. So if we would be able to make this DFA, it will be a more elaborate DFA, and furthermore, the input alphabet is much more elaborate. Given an atomic formula in Presburger arithmetic in I variables, what can we do? Well, we will define sigma I to be the alphabet with 2 to the I characters. We will think of each symbol in this alphabet as a column which contains I bits. The first entry in this column is the bit of the first variable. The second entry in this column is the bit of the second variable, all the way up to the ith entry in this column, which is the last entry, is a bit of the last variable x sub I. So using this more elaborate alphabet, every string of this alphabet will correspond to I numbers, which we can call A1 up to AI. Once again, using the same trick as we did in designing the previous DFAs, we can design a new DFA. This DFA will accept a string if and only if it corresponds to I numbers that satisfy this atomic formula. So our goal is to make a DFA D such that D accepts S if and only if A1 up to AI satisfy the equation F. As long as F is an atomic statement in Presburger arithmetic, we can make a DFA that does this. So what we can do is we can look at atomic formulas in Presburger arithmetic and capture them with DFAs. That's a very powerful fact. But what about non-atomic formulas? What about formulas which use other operators like AND, or not? And what about quantified formulas? Well, let's have a look and see if we can also capture them by DFAs. Let's start with a simple case first. Let's look at this first formula, which is x1 plus x2 plus x2 plus x2 equals x3 plus x3 plus x4 plus x5. We have another atomic formula, which is x1 plus x2 plus x3 plus x5 equals x4 plus x4 plus x4. We know that we can make a DFA D1 that accepts strings over this alphabet sigma 5 star in the first case, and DFA D2 that again accepts strings over the alphabet sigma 5 star. So in some sense, these DFAs capture the atomic formula of Presburger arithmetic. Well, what about non-atomic formulas? So let's make a non-atomic formula which is made out of these two atomic formulas. One way to make a non-atomic formula is to take the first formula and OR it with the second formula. Another way to make a non-atomic formula is to take the first formula and AND it with the second formula. The third way to make an atomic formula is, for example, we can just negate the first formula, and of course we can make a much more complicated formula by negating the first formula and then ORing it with the second formula. Can we make DFAs which capture these formulas? So can we make DFAs which will accept strings over sigma 5 star, and they will accept strings if and only if the 5 numbers corresponding to a string of sigma 5 star satisfy these formulas? Well, you know from automator theory that regular languages are closed under unions. They're also closed under intersections and complementations. And in fact, if you give me two DFAs, I can easily make a new DFA by looking at those two DFAs, which accepts the union, whose language is the union of the languages accepted by these two DFAs. I can also easily make another DFA which accepts the intersection. If you give me a DFA, I can easily make another DFA which accepts the complement of the language of the given DFA. Regular languages are closed under unions, complements, and intersections. And we have very simple algorithms which can actually take two DFAs and output a new DFA which accepts the union of the languages of those two DFAs. So we can use those ideas to come up with DFAs that actually accept these formulas. In the first case, we will make a DFA that accepts all the strings that are accepted by D1 or D2. Well, regular languages are closed under union, and that solves the first problem, the first formula. They're closed under intersection, and that solves the second problem, and they're closed under complementation. So we can make DFAs that accept all strings which represent numbers which satisfy a formula in Presburger arithmetic, as long as that formula has not used any quantifiers. So what have we shown? Let's look at it. Given a quantifier-free formula f in I variables, we define sigma I to be an alphabet with 2 to the I characters, and now each string in sigma I defines I numbers. We can make a DFA D such that D accepts S if and only if A1 up to AI satisfy this formula. So we can capture all quantifier-free formulas of Presburger arithmetic using DFAs. Well, let's go further. What about formulas with quantifiers? Let's look at one of them. It is, there exists x3, x1 plus x2 plus x2 equals x3. This formula has two free variables, x1 and x2. So if we want to capture this formula, we will have to use sigma 2. So what we want to do is use sigma 2 because x3 is a bounded variable, it's not a free variable, and once again we want to capture this formula with some kind of a DFA. Can we make a DFA-D that accepts strings S in sigma 2 star such that S represents x1 and x2 which satisfy this formula? Well, what we know is that we can make a DFA-D that accepts strings in sigma 3 star such that S represents x1, x2 and x3 which satisfy x1 plus x2 equals x3. So if we look at the quantifier free part of this formula, we can capture that with a DFA. But that's not what we want. We want to capture the whole formula with the quantifier. What we would like is to make a new DFA D prime such that it accepts strings S prime in sigma 2 star such that S prime represent x1 and x2 that satisfy there exists x3, x1 plus x2 equals x3. So we have a DFA which accepts strings over sigma 3, but it does not capture the quantified part of this formula. What we would like is a new DFA which captures strings over sigma 2 and captures the whole formula. It is possible to make a DFA, but it is much easier to make an NFA using the given DFA. The NFA N is simply going to guess the value of x3 as it goes along moving to the right. Thus, in each move, it makes two non-deterministic moves. One pretending that the current bit of x3 is 0 and the other pretending that the current bit of x3 is 1. Once we have this NFA N, we can convert this to a DFA using a standard algorithm. So what we do is, instead of trying to make a DFA, we make a NFA. We have a DFA-D which accepts strings over sigma 3 star. Now, instead of making a DFA-D prime, we make a NFA which accepts strings over sigma 2 star. Remember that the symbols of sigma 3 are columns of size 3, the symbols of sigma 2 are columns of size 2. So when you read a symbol of size sigma 2, you can think of it as a symbol of sigma 3 with the last entry missing. Now what this NFA does, it fills that entry by guessing what this bit is going to be. One guess is going to be 0 and the other guess is going to be 1. And then it behaves exactly like the DFA-D, as if it were operating on a string of which belong to sigma 3 star. And this way we can make a NFA which captures this quantified formula. We can deal with quantifiers like this one by one. Let us say that we have a formula phi which is there exists xi psi. We will first make a DFA-D that accepts all those strings over sigma I star that represent x1 up to xi and satisfy psi. So they will satisfy psi, the inner part of this formula. Then we'll make a NFA that uses D and guesses the each value of each single bit of xi as it goes along. Then we use a standard algorithm to convert this non-deterministic finite automata N to D. And now D will accept strings over sigma I minus 1 star. So using this standard trick, we can also capture quantified formulas. However, I've only told you how to capture quantified formulas when the leading quantifier is there exists. We also have to deal with one more quantifier, which is for all. So how do we deal with the quantified formula if the leading quantifier is for all? Let's see how to handle universally quantified formulas. Let us start with the formula phi, which is equal to for all xi psi, and psi is a smaller formula. So the variable xi is a bounded variable and the quantifier associated with it is the universal quantifier. What we can do is we can convert this formula for all xi psi into a new formula which is not of there exists not of psi. So in other words, we use this other formula, which is not there exists xi not of psi. Using De Morgan's laws, which you must have studied, we know that these two formulas are equivalent. These two formulas are equivalent by De Morgan's law. De Morgan's law says that not of for all is the same as there exists not. So as you push the negations across quantifiers, they change. A universal quantifier becomes an existential quantifier, and an existential quantifier becomes a universal quantifier. So using this trick, using De Morgan's laws, we can change all universal formulas to existential formulas, but we will have to deal with negation. How do we now make this NFA? Well, we can use the same trick for dealing with the existential quantifier. All we have to do is just ask ourselves, how do we deal with negations? Well, dealing with negations is very easy. Once again, we know regular languages are closed under complementation, so we can make a machine that captures that formula and take another machine which accepts the complement of that language, and we would have captured this formula. So the whole procedure is as follows. We first make a DFAD that accepts all those strings over sigma I star that represent x1, x2 all the way up to xi and satisfy psi. This we can use the fact that regular languages are closed under complementation, and we make a DFAD prime that accepts phi. We can also use the technique for handling there exists, and after doing that we complement that DFA to eventually get our final DFA. This is the procedure for handling universally quantified formulas. Now let's see, where does this all lead to? What have we eventually proved? Suppose now that we have a sentence over Presburger arithmetic. So we have a sentence which is a formula which does not have any free variables. We can use the techniques that we have studied now to actually remove quantifiers. We go to the end part of it and we get a formula which is I variables. We capture that formula using a DFA. Then we add one quantifier to it. That quantifier becomes bounded, that variable becomes bounded. The number of variables in the formula reduces by 1, and using the previous technique, we capture that formula. We keep repeating this. It really doesn't matter if the quantifier is existential or universal. We can deal with them one by one. What would this eventually lead us to? This way we have taken a sentence, a general sentence, q1, x1, q2, x2 all the way up to qi, then phi, which is in premixed normal form, and we've made a DFAD that will accept the empty string over sigma 0 if and only if this formula were true. So we have been able to capture a whole sentence in a DFA. This DFA will accept the empty string if and only if this formula is true. Now we simply run this DFA on the empty string, and if it accepts the empty string, we say that the formula is true, and if it does not accept the empty string, we say that the formula was false. So our decision algorithm is quite complicated. The algorithm is to make this DFA from the formula and then eventually see if this DFA accepts the empty string or not. This shows that Presburger arithmetic is decidable. If you give any formula, any sentence over Presburger arithmetic, we can tell whether the formula is true or not, and we actually have an algorithm for telling whether the formula is true or not. In the next lecture, we will look at undecidability of logical theories. We would actually prove that number theory with multiplication, the Peano axiom with Peano axioms is not decidable. I'll see you next time. Thank you and goodbye.